Stephen Hawking was the most famous scientist alive. He had written a book that sold 10 million copies. His synthesized voice was instantly recognizable to people who had never opened a physics textbook in their lives. When he walked into a room, or rather when his wheelchair moved through a doorway, conversations stopped, not out of pity, out of genuine earned reverence. Because this was a man who had looked at the universe longer and more carefully than almost anyone else alive, and what he had seen had transformed physics permanently. He was also on one of the most important questions in modern science, completely wrong. And for more than 20 years, almost nobody believed the man who said so. That man was Leonard Susskind, a theoretical physicist from Stanford. A kid who grew up in the South Bronx, son of a plumber, who taught himself mathematics from library books, clawed his way into theoretical physics on sheer intellectual stubbornness, and eventually became one of the fathers of string theory. A man who sat in a room in 1981 listened to Hawking make an argument that most of the greatest physicists of the generation accepted without serious challenge, and felt something cold move through him that he would later describe in his own words as a kind of physical dread. Not disagreement, not skepticism. Dread, because Susskind understood immediately what the implications were. If Hawking was right, if what Hawking was claiming was actually true, then it was not merely a strange quirk about exotic astronomical objects. It was a fracture running through the foundation of all of modern physics. And the fracture was deep enough to collapse everything built on top of it. This is the story of what happened next. 20 years of one of the most intense intellectual battles in the history of science. Two incompatible visions of reality. One question at the center of everything: what happens to information when it falls into a black hole? The answer changed physics forever, and the universe it revealed is stranger than either man expected. Before the war can make sense, you need to understand what was actually at stake, because on the surface this looks like an argument about black holes, about extreme objects at the farthest edges of the observable universe, about physics so remote from everyday experience that it seems to have no connection to anything that actually matters. But that is not what it was about. It was about the deepest law in physics. The law that everything else depends on. The law that, if violated, does not just break one equation or one theory or one prediction. It breaks the entire framework of modern science from the ground up. That law is called Unitarity. And what it says in plain language is this: information cannot be destroyed. Think about a fire. You take a newspaper and burn it. The words vanish. The paper turns to ash and smoke and carbon dioxide. You cannot read the newspaper anymore. The information appears to be gone. But every single atom that was in that newspaper before the fire is still somewhere in the universe after it transformed into ash, into gas, into heat radiating away into the room. The information about every molecule of ink, every fiber of paper, every quantum state of every particle, it is still there. Scattered, scrambled, essentially impossible to recover in practice, but never actually erased. In principle, with unlimited knowledge and unlimited computing power, you could trace every atom forward from the moment before the fire and reconstruct the complete quantum state of the newspaper. This is unitarity. The total quantum information of a closed system is conserved. It can be redistributed, it can be scrambled beyond any practical hope of recovery, but it cannot be annihilated. Without unitarity, quantum mechanics collapses. Probabilities stop adding up correctly. The wave function loses its mathematical integrity. Cause and effect become undefined. Every successful prediction that quantum mechanics has ever made, and it has made more successful predictions to more decimal places than any other theory in the history of science, depends on unitarity being true without exception. Hawking said black holes are the exception. He said information does not just get scrambled when it falls into a black hole. It gets destroyed permanently, irrecoverably, removed from the universe as completely as if it had never existed. To understand why Hawking believed this, you need to understand what he had discovered just a few years earlier, a discovery so brilliant that it had already made him the most celebrated theoretical physicist of his generation. In 1974, Stephen Hawking did something nobody expected was possible. He combined quantum mechanics and general relativity, two theories that had resisted every attempt at unification, in a single calculation applied to black holes. And what he found stunned the physics community. Black holes are not completely black. They glow. A slow, steady, almost imperceptible radiation leaks away from just outside the event horizon, the invisible boundary past which nothing can escape, caused by quantum effects at the edge of the extreme gravitational field. Pairs of virtual particles pop into existence from the quantum vacuum near the horizon. One particle falls inward past the boundary, the other escapes outward into space. The escaping particles carry energy away from a black hole. The black hole loses mass. Given enough time, truly astronomical amounts of time, far longer than the current age of the universe, for any black hole of significant size, the black hole shrinks and eventually evaporates completely. This is Hawking radiation. It remains one of the greatest theoretical discoveries of the 20th century. It told us that black holes are not eternal. They have a temperature. They have a lifetime. They participate in thermodynamics in ways nobody had imagined. But Hawking noticed something deeply troubling about the radiation he had just discovered. It is thermal, completely thermal, random, structureless, like the heat radiating from a warm rock sitting in an empty field. It carries no information about what created the black hole or what fell into it afterward. The quantum state of the outgoing radiation depends only on the mass, charge, and spin of the black hole as a whole, not on the specific details of the star that collapsed, not on the encyclopedia that fell in afterward, not on the quantum states of any of the particles that crossed the event horizon. In 1976, Hawking published this conclusion formally. He called it the breakdown of predictability in gravitational collapse. What it meant was stark and simple. A black hole evaporates through thermal radiation that carries no record of what it consumed. At the end, the black hole is gone, and the information about everything that ever crossed the horizon has been permanently erased from the universe. Not scrambled, not hidden, erased. This was a direct, explicit mathematical statement that unitarity is violated in the presence of black holes. That information can be destroyed. That quantum mechanics, the most successful theory in the history of physics, breaks down at the event horizon of a black hole. Hawking said this in 1976. He repeated it at a conference in 1981. Both times, the majority of the physics community nodded along because this was Hawking. And because the calculations seemed airtight, Susskind was at that 1981 conference. And he drove home afterward in a state he has described as barely functional, filling pages with equations in the early morning hours, searching obsessively for the flaw in Hawking's argument, finding nothing immediately obvious, and feeling underneath all of it a certainty that refused to go away no matter how solid the calculation looked. Hawking was wrong, something was wrong, and Susskind was going to find it. The first counterattack came in 1983. Working with Thomas Banks and Michael Peskin at Stanford, Susskind asked a simple but devastating question, not whether information was destroyed, but what the universe would actually look like if information destruction were a real physical process. The answer was catastrophic in a way that went far beyond black holes. Microscopic virtual black holes do not just appear in the vicinity of astronomical objects with enormous mass. They flicker in and out of existence, constantly in the quantum vacuum, in empty space everywhere, all the time, right now, all around you. The uncertainty principle permits brief, violent fluctuations in the geometry of spacetime at the smallest scales. These fluctuations include structures that briefly have the geometry of black holes, appearing and dissolving in intervals so short they cannot be directly observed but are entirely real in their physical effects. If information destruction is a genuine property of black holes, if it is a real physical process permitted by the laws of nature, then these microscopic virtual black holes are destroying information constantly everywhere, every point in space, without stopping. Banks, Susskind, and Peskin calculated what a universe with this property would look like. The vacuum of space would heat to temperatures so extreme that the number has no physical meaning. Not warm, not hot, not the temperature of a star or the center of a nuclear explosion. A temperature so incomprehensibly large that it would render all structure in the universe instantly impossible. Matter could not exist. Atoms could not exist. Space itself would be a seething, infinitely hot chaos with no structure whatsoever. And yet here we are in a universe that is, by every measurement we have ever made, extraordinarily cold. The cosmic microwave background, the faint thermal glow filling all of space left over from the early universe, sits at 207 Kelvin, just barely above absolute zero, a universe of breathtaking order and structure and complexity. That is not what a universe with information destruction looks like. That is not even close. The calculation did not prove Hawking wrong, but it proved that Hawking's conclusion was incompatible with the universe we actually inhabit. Something in the chain of reasoning had to be wrong. The question was where the error was hiding. Susskind published this. He argued it loudly and persistently at every conference he attended for years. He presented it to rooms full of physicists who largely remained unconvinced, because Hawking was Hawking, and because the flaw in Hawking's original calculation had not yet been found. the war continued. The answer that eventually won the war did not come through a single decisive calculation. It came through a series of ideas that built on each other over more than a decade, each one more radical than the last, until the final picture was so strange that it rewrote the nature of space itself. The first major breakthrough came in 1993. Working with Larousse Thorlacius and John Uglum, Susskind published a paper introducing a concept he called black hole complementarity. The paper came from a meeting where Susskind had told his colleagues that he wanted to say something bold enough to genuinely shake things up. What they proposed was certainly that the setup requires a thought experiment. An astronaut, call her Alice, falls into a black hole. What happens to her? From Alice's own perspective, crossing the event horizon is completely unremarkable. General relativity is clear on this point. The event horizon is not a wall. It is not a surface with any locally detectable physical property. It is simply a boundary in space defined by the global structure of the gravitational field. A freely falling observer moving through it experiences nothing special at the moment of crossing. Alice falls through the horizon and continues toward the singularity at the center, experiencing ordinary physics all the way to the inevitable end. But from the perspective of an observer watching from far outside, call him Bob, something completely different happens. To Bob, Alice never crosses the horizon. General relativity and quantum mechanics together predict that, to a distant observer, in falling matter appears to slow down asymptotically as it approaches the horizon. Its image increasingly redshifted, its signals stretch to longer and longer wavelengths. From Bob's perspective, Alice gets encoded on the surface of the event horizon, heated by the intense radiation near the boundary, and eventually re-emitted as Hawking radiation. Her information never crosses inside, it comes back out, two completely different physical descriptions of the same events. Alice experiences falling through the horizon. Bob sees Alice get encoded on the surface and re-emitted. Both descriptions are internally consistent. Both are supported by the mathematics, and they are completely incompatible with each other. This sounds like a fatal contradiction, but Susskind's insight was that it is not because Alice and Bob can never compare notes. The structure of the event horizon makes it permanently and physically impossible for any single observer to access both descriptions simultaneously. Alice inside cannot send signals to Bob outside. Bob outside cannot receive any information from Alice after she crosses. No experiment, no measurement, no physical process of any kind can ever bring the two descriptions into direct conflict. The universe never has to choose between them. Both are simultaneously valid, permanently separated by the horizon. Information is not lost inside, it is encoded on the surface. Both are true, and no contradiction arises because no observer can ever be in a position to observe both simultaneously. In the same year, the Dutch physicist Gerard de Hooft took the complementarity idea and extended it into something even more radical. He proposed that everything that falls into a black hole, every particle, every quantum state, every bit of information about everything gets encoded on the two-dimensional surface of the event horizon, not in the interior. Not at the singularity, on the boundary, on the surface. The mathematical basis for this came from Jacob Bekenstein's work 2 decades earlier. In 1972, Bekenstein had shown that black holes carry entropy, thermodynamic disorder, proportional to the area of their event horizon. Not the volume, the area. Each Planck scale unit of surface area encodes exactly 1 bit of information. The entire information content of a black hole, regardless of what it contains, regardless of how complex, is fully specified by what is written on its two-dimensional surface. Hooft and Susskind extended this into what Susskind called the Holographic Principle. If the information content of a black hole is encoded on its two-dimensional surface, and if black holes represent the maximum possible information density for any given region of space. The same must be true of any region of space. The maximum information content of any volume is set not by the volume, but by the area of the surface surrounding it. 3 dimensions of space can be fully described by 2. The interior is a projection of the boundary. Reality is holographic. This was the conceptual weapon that would eventually end the war, but it needed mathematical proof. And that proof came in 1997 from a 29-year-old Argentinian physicist named Juan Maldacena. Maldacena published what became the most cited paper in the history of theoretical physics. He demonstrated an exact mathematical equivalence not an approximation, not an analogy. In the sense of precise equality between a full theory of quantum gravity in five-dimensional curved spacetime and a quantum field theory with no gravity living on the four-dimensional boundary of that space. Two completely different theories, identical in every calculation. The same physics written in two different mathematical languages. And crucially, the boundary theory, the one with no gravity, had no information paradox. Information was manifestly, provably preserved, which meant it had to be preserved in the gravitational theory too. Inside black holes, every time without exception, the mathematics had closed the door that Hawking's argument had tried to open. On July 21st, 2004, Stephen Hawking stood at the front of a conference hall in Dublin, Ireland. On that day, he gave a talk at a conference in Dublin, Ireland, in which he announced that he was conceding the bet he had made with physicist John Preskill in 1997, that information was lost in black holes. After concluding his talk, Hawking presented Preskill with the 8th edition of Total Baseball, the ultimate baseball encyclopedia, from which information can be retrieved at will. 23 years after that conference in 1981, where Susskind first felt the dread settle into his chest, 23 years of papers, arguments, calculations, counter-arguments, and competing visions of reality, ended with a synthesized voice in a conference hall saying the three words that no physicist of Hawking's stature says easily: I was wrong. But I want to stay with something that the victory and the concession, dramatic as they are, can obscure the predominant belief among physicists since the ADS-CFT correspondence is that information is indeed preserved in black hole evaporation. The dominant idea is that Hawking radiation is not precisely thermal, but receives quantum correlations that encode information about the black hole's interior. But the precise step-by-step physical mechanism, the exact account of how every quantum state of everything that ever fell into a black hole gets encoded in the outgoing Hawking radiation, that remains one of the deepest unsolved problems in theoretical physics today. The resolution is that the information is not lost, but it is scrambled in a way that makes it nearly impossible to retrieve. Scrambled to a degree so extreme that recovering it would require a computational effort so vast it makes every calculation ever performed in human history look trivial by comparison, but not erased, never erased. The war ended. The paradox was resolved in principle, but the details of the mechanism are still being worked out, and underneath those details is something even more vertiginous. If the holographic principle is correct, if the three-dimensional world is genuinely a projection from a two-dimensional boundary, then the war between Susskind and Hawking was not just about black holes. It was about the nature of space itself. It was about whether the depth and volume of the physical world are fundamental or emergent. It was about whether the universe we inhabit has the structure we think it has. Susskind's answer to Hawking turned out to be more radical than the question that provoked it. Information cannot be destroyed, not by fire, not by time, not by the most powerful gravitational force in the known universe, not by the crushing singularity at the center of a black hole. The universe maintains a complete and perfect record of every physical event that has ever occurred, encoded in forms we are only beginning to understand. Hawking was wrong. Susskind proved it. And the universe they were arguing about is stranger, deeper, and more beautiful than either of them fully imagined when the war began.